Hey guys, we're back today with a video on superposition. We already touched upon this in a little in earlier videos, but I thought we would dive a little deeper into it. I'm excited, I hope you are. Let's hop right into this video. So basically, quantum superposition is the fact that quantum particles can have multiple states at once. Whoa, wait, what? Like, be in two different locations, have two different velocities, and have two different energy states? Yeah, and much more. It's important to note that this only applies when we are not directly looking at or measuring the system. So to put this in an example, let's say we're looking at an anthill. There is a huge network of tunnels underground, and there are only 2 points of entry into the network. We can see an ant crawl into one hole, and we can see it come out of the other. Now, in classical physics, we can assume that the ant took one tunnel, one distinct pathway, to reach the endpoint and resurface. However, in quantum mechanics, what happens is that the ant, until we look at it, is actually taking every pathway simultaneously. Seems crazy, right? Yeah, I struggle with this one too. Let's repeat the same experiment. However, let's watch the ant as it crawls through. Well, unfortunately, that alters what happens. Instead of being in superposition, observing the system forces the quantum particle to pick a state at random to follow. We can set up the experiment and find results, but we can't see the process. As annoying as this is, it holds true when tested. A famous experiment of this is the double slit experiment. We have a machine that fires a stream of electrons through a sheet with 2 vertical slits in it, finally landing on a full sheet behind the first, where we detect where the electrons land. If something, like a bunch of marbles, were shot through the 2 slits, we would see a pattern reflecting 2 vertical bars right behind the slits. However, if a wave was sent through the slits, we would see an interference pattern. This happens because when a wave passes through a small opening, it radiates out from it as if the slit becomes the new center of a ripple going in that direction. When the radiating wave of one slit collides with another, the waves cancel out, where one is at a high and the other is at a low. So we are left with the times when the wave amplitude adds up and when the waves cancel each other out. This interference pattern generates many vertical bands when seen on the final sheet. So particles, like the stream of electrons for instance, behave like marbles, right? Well, they don't. They behave like the waves, generating the same interference pattern. Shoot, how does this happen? Well, the explanation is that the electron, when fired, leaves as a particle, but then becomes a wave of potentials, passing through both slits, and then interferes with itself as it goes past the slits and hits the wall, as a particle once more. There are 3 possible ways an electron in classical physics could behave. It could go through the left slit, the right one, or neither. However, in quantum mechanics, superposition tells us that all of these possibilities happen simultaneously. The result is it could go through the left, the right, none, or both at the same time. The electron takes every possible path, ending up with a wave-like interference pattern as a result. Ready to be really annoyed? Well, as soon as we try to detect it mid-path to see which slit the electron really passes through, it changes our outcome. The electron, as if it knows it is being observed, chooses one of its superimposed pathways at random. As soon as we put up our detector at the slit, we see the resulting pattern on the full sheet change into two vertical bars, as if they act as marbles again, just normal particles. No more interference pattern. If you are confused or anything, don't worry. It's weird stuff. So why don't we take a look at another example of superposition? Another way to show this is in a famous thought experiment you've probably heard of, Schrodinger's cat. The details of the setup are unfortunate for the cat, which ends up having a 50% chance of being killed by poison due to radioactive decay within the first minute it's put into the box. Isn't that just heartwarming? No, but this is a pretty good showcase of quantum superposition, because we can't tell if the cat is dead or alive until we look. In classical physics, we know that it is either dead or alive, but quantum mechanics dictates that the cat is both dead and alive simultaneously. And until we look, it will remain that way. When we look, the system chooses a random state to be in, so we may open the box and see the cat living or see it dead, but until we do, it remains that the cat is both alive and dead. If you think this sounds ridiculous, technically you're on the same side as the creator of this thought experiment, Erwin Schrödinger, who coined it to show the absurdity of the current view of quantum mechanics at the time. Yet, it remains as a model showcased now over 80 years later than its creation. So after this is all said and done, we are left with superposition remaining a fact of quantum mechanics. Multiple states all superimposed over one another, creating simultaneous outcomes. Until we look at the system, every outcome remains not only possible but certain. However, the observation of the system mid-path forces it to choose a singular state at random, changing the recorded outcome of the experiment. Quantum particles, by nature, do not like to be watched. Unlike my other videos, be sure to check them out. For now though, thanks everyone for watching. Leave a like if you enjoyed. I hope to see everyone in the next video. Bye-bye.